We're going to take a look at the second case of graphing derivative functions, or graph a function given another graph. Case 2 is graphing f double prime of x given f prime of x. So we're going from f prime to f double prime. Now remember, we talked about the fact this the same steps as going from f to f prime, simply because f double prime is the derivative of f prime, just like f prime is the derivative of f. So we're going to be in the same exact steps for case 2 to different step one, case 1. Here's our graph. It's just kind of a preliminary visual of what we're going to be doing. We'll be looking at decreasing and increasing. We're going to be looking at concavity, vertical tangent lines, everything we looked at when we went from graphing f to f prime. Following is the graph of f prime of x. Use the graph of f prime to sketch the graph of f double prime, the second derivative of f of x. So here it is. It's a very strange looking graph. It starts out shallow, decreasing, and it starts to increase somewhere around there. Then we have a vertical tangent at x equals 0. Then it continues to increase. However, the slopes of the tangent lines are decreasing there, so it changes to concave down. So we will keep all of that in mind as we graph f double prime of x given f prime of x. All right, jumped a little bit there. Step 1, where is f prime of x decreasing? So if we look at this graph, it's decreasing up until about -3. It will start to increase. So we will just write from -infinity to -3. Now again, this same steps is going from f to f prime. So this means that f double prime will be below the x-axis from -infinity to -3 because the slopes of the tangent lines are negative, and f double prime is the slopes of the tangent lines of f prime. So step 2, f double prime will be negative between -infinity and -3 because that's where f prime of x is decreasing. In the same way, we will look at where f prime of x is increasing. So after -3, it will increase. Now, it's important to note that wherever you have a vertical tangent, that's not technically increasing. So we're going to go from -3 to 0, and then start back again at 0 to infinity. This will tell us that the graph of the derivative will be increasing on these intervals. Step 4, f double prime of x is positive because it's going to be positive from -3 to 0 and 0 to infinity because f prime of x is increasing there. And again, f double prime of x is the derivative of f prime of x. Next, we're going to figure out where does f prime of x have horizontal tangent lines. For step 5, this has a horizontal tangent right here. If we were to draw a tangent line at -3, it would go straight across, and therefore at x equals -3 we have a horizontal tangent. What does this mean for f prime of x? Well, it means it's going to have an x-intercept at -3, 0, because f prime of x has a horizontal tangent there, meaning the slope is 0, so the y value of f prime of x, f double prime of x is going to be 0. That's going to be at -3, 0, so it will have an x-intercept there. Okay, next, where does f prime of x have vertical tangents or cusps? So at x equals 0, we have a vertical tangent for f prime of x. So what do you think that's going to mean for the second derivative? Remember that the second derivative is the slopes of the tangent lines of the first derivative. So since it has a vertical tangent here, that means the tangent line basically approaches infinity, right, from the left and right. So it means the second derivative graph will approach, the y values will approach infinity since they are the slopes. So we're going to have an asymptote right there. So for step 8, f double prime of x has asymptotes. It has a vertical asymptote because f prime of x has a vertical tangent there, and i.e. that's where a place where the slope of the tangent line approaches infinity. So that's helpful. Anytime you have a asymptote, it's really going to help you graph the function. Step 9, where does f double prime of x have sharp edges? Well, this one doesn't have any, but remember, whenever it has a sharp edge, there's going to be a hole for the next graph, or the derivative graph. But in this case, No holes, so for step 10, f double prime of x will have no holes because f prime of x had no sharp edges. Step 11, where is f prime of x concave down? Well, we can see it's concave down from 0 to infinity, meaning the slope of the tangent line is decreasing. And because of that, that means that f double prime of x will be decreasing from 0 to infinity. Step 12, f double prime of x is decreasing on the interval 0 to infinity because f prime of x is concave down there, and therefore the slopes of the tangent lines are decreasing. In the same way for step 13, whereas f prime of x concave up, it's going to be from negative infinity to 0, meaning the slopes of the tangent lines are increasing. Okay, even though it's negative, it's getting less and less and less negative, and then it becomes positive. So therefore, it's concave. F prime of x is concave up from negative infinity to 0, meaning that's where f double prime of x will be increasing for step 14, because f prime of x is concave up, and therefore the slopes of the tangent lines are increasing. Next, for step 15, we want to where does f prime of x go from concave down to concave up? Well, never, but remember, if it does go from concave down to concave up, then the next derivative, in this case f double prime, would be going from decreasing to increasing. It would have a relative minimum. However, this does not occur because there is never a transition from concave down to concave up for f prime. So f double prime will not have a relative minimum. But for step 17, where does f prime of x go from concave up to concave down? It happens right here. Because of that, we have a possible relative max. Now, here's the thing though. They have a vertical tangent here, okay? So just because the f prime of x goes from concave up to concave down doesn't necessarily mean that the derivative graph is going to go from increasing to decreasing continuously. Okay, remember, it has to be continuous. And we can see it's not because the change in concavity here, we have a vertical tangent here. And so that's actually not technically going to be continuous for the derivative, right? The derivative won't exist there, so it can't have a relative maximum. So for step 18, f double prime of x will have a relative maximum, but there's a caveat. Although f prime of x transitions from concave up to concave down, x equals 0, the tangent line is undefined here, and therefore f double prime of x has no relative maximum. So make sure there's a point there that exists. Step 19, where does f prime of x have the steepest negative? I do want to make one more note about that. Okay, so just make sure this point exists. Again, I've said that already, but make sure the point for the derivative exists. In other words, if it doesn't exist, then it can't be a relative min-or-max there. Okay, where does f prime of x have the steepest negative tangent line? Well, just based on the window we have here, it's going to be at negative 10 because the tangent line is increasing there, so it's going to be less negative, and it's certainly positive here. So when we graph our f double prime, this will have an absolute minimum here because at negative 10 it has the least steep tangent line. At x equals negative 10 for step 20, f double prime of x will have an absolute minimum because f of x has its smallest slope of the tangent line. We should say f prime of x. Okay. Now you might be thinking, well, what's the y value there? Well, all you have to do is kind of take a look and see what you think the slope of this line is and kind of estimate it. And a lot of times when I'm drawing the tangent line, I get it wrong the first time. The thing is, it's going to be very slight, okay? It's going to be like a negative fraction, maybe something like negative 1/4. We can kind of guess by picking 2 points on this line. Yeah, it's going to be a very negative fraction. It's going to be pretty close to, we'll say negative 1/4. So that point might be something like negative 10, negative 1/4 on the f double prime graph. Okay, so step 21, where does f prime of x have the steepest positive tangent line? Well, right here, it goes from infinity to something really big, so it's not going to have an absolute maximum for the derivative because second derivative, because the first derivative doesn't have an absolute steepest tangent line. So f double prime of x will not have an absolute maximum because f prime of x increases without bound. Particularly right around 0, we can see the tangent line is pretty close to infinity, everything but infinity. So f double prime of x is not going to have an absolute max. All right, next we're going to plot our points and asymptotes. Now, we already said there's an asymptote at x equals 0 because f prime of x had a vertical tangent. We just now found a point at -10, -1/4 being an absolute minimum. And we also found, let's get a check here real quick. We also found an x-intercept at -3, 0. Okay, so we don't have a lot here, but we do have enough to come up with a graph, and here's why. We know our increasing, decreasing intervals. We know our concavity intervals. So let's take a look. So first of all, we know that the graph we know that f double prime of x is going to be below the x-axis from -infinity to -3 because f prime of x is decreasing there. Furthermore, we figured out that it's going to be, well, actually, let's just put this together with concavity and increasing. We also know that it was concave up from -infinity to 0. So our graph of f double prime of x will be increasing. So we can put those together and draw the first part of the graph. Okay, it's going to be below the x-axis from -infinity to -3. It's going to cross through that absolute minimum, but it's going to increase the whole time up until our asymptote. That's pretty simple, right? There's really only way to connect that line, and of course it's going to hug the asymptote. Next, we figured out that it decreased from 0 to infinity, and we figured out that, let's take a look, I believe it's going to be above the x-axis all the way. Yeah, it will be above the axis from 0 to infinity as well. So, it will be decreasing. It will be decreasing, but above the x-axis from -infinity to 0. And again, we figured out it was going to be above the x-axis because f prime of x was increasing there. But we figured out ultimately it was going to be decreasing because f prime of x was concave down there. So you can have a function that decreases but still positive. And that's exactly what we're going to do to finish out this graph. So we put all that together, and there's only one way to sketch it. And again, the derivative doesn't look very much at all like the original. Let's take a closer look. So here's the original graph. We can see that wherever it decreases, the f double prime of x will be below the x-axis, and where f prime of x increases, f double prime will be above the x-axis. Next, we see that wherever f prime has an extrema, f double prime will have an x-intercept. Wherever f prime of x is concave up, f double prime will be increasing. And wherever f prime of x is concave down, f double prime of x will be decreasing. Next, wherever f prime of x has an inflection point, f double prime will have a possible extrema, but again, because that's a vertical tangent, the second derivative will not have an extrema point there. So that's it in a nutshell. You can see that, again, second derivative graph doesn't look much like the first, but as long as you follow your steps, use all of this information available, you can come up with a pretty accurate graph for f double prime given f prime. If you have any other questions about this lesson, let me know.